I want to start this video by looking at a example, not from linear algebra, but just from a very simple algebraic equation. I want to look at the equation, let's say 7x is equal to 14. Most of us can look at this and immediately say, oh, well, x has to be equal to 2. But I want to think about the process that we go through to get there. The most direct way is we can divide both sides of the equation by 7 to get x is equal to 2. However, if we want to be able to relate this to a matrix equation where the number 7 is going to play the role of a matrix, I can't use this method because I can't divide by a matrix. That's not a defined thing. So instead of this, I could think of this as let's multiply both sides of this equation by some number, 1/7. When I do that, I get again x is equal to 2. Because really I'm doing the same thing. This is still a problem though, because this would require some form of a division of matrices to come up with this number 1/7, the identity divided by our 7 matrix. That isn't allowed. That can't be done. So what we can think of instead is if I have 7x equal 14, I can think of the multiplicative inverse, which we write as 7 to the negative 1, which in the case of a number is just 1/7. But in the case of a matrix, we're going to see if we can come up with some kind of a corresponding inverse for a matrix. So normally we would say that when you multiply two matrices, you can't switch the order. But let's suppose for a second that we have some matrix A and we have a matrix C that is the inverse. So if I take C times A, what does it mean to be the inverse? It means that when I multiply them together, I'm going to get the identity. Just like 7 times 7/1 is equal to 7 times 1/7 is equal to 7/7 is equal to 1. It gives you the identity. And the thing that is nice about inverse matrices is if C is an inverse matrix, then CA is equal to the identity and AC is equal to the identity. That is to say, A and C are inverses of each other. So the order doesn't matter. So let's suppose we have some matrix A and both B and C are inverses of matrix of A. Then I can start with the matrix B and I can multiply B times BI, multiply it by the identity matrix, and nothing changes. So that is still valid. Because C is an inverse matrix of A, I can replace the I with AC. But I can do the first multiplication first instead. I can reorder my multiplications to get BA times C. And because B is the inverse of A, this is equal to the identity matrix times C, which is just equal to C. So all in all, what we get is that if we have two inverse matrices, B and C, then B is equal to C. That is, they're the same thing. So if you have two inverse matrices, they have to be the same, which means that A has only one inverse. So any matrix A has at most one inverse matrix. From now on, we will denote that A inverse. Now, not every matrix has an inverse matrix, but If you have an inverse matrix, if the matrix is invertible, then every inverse matrix is the same. So we can use just A inverse instead of having to say, oh, well, B is an inverse matrix of A, and things along those lines. So this allows us to simplify our notation so that we only refer to the inverse instead of saying this inverse or that inverse. Now, I want to think about, I don't know what just happened to my, I'm not sure what just happened to my screen. Sorry about that. Okay, so I want to think about how do we actually calculate some of these, an inverse matrix. So we're going to start with the simplest setting we can come up with. So let's let A be the matrix A, B, C, D. So it's a 2 by 2 matrix. And I want to find an inverse matrix. I don't know what that is, so I'm going to just write it as E, F, G, H. But if this E, F, G, H matrix is the inverse of A, B, C, D, then I know this has to equal the identity matrix 1, 0, 0, 1. Now, if I put that together by carrying out the multiplication, I see that going across the first row and down the first column, AE plus BG must be equal to 1. Across the first row and down the second column, AF plus BH has to equal 0. Across the second row and down the first column, CE plus DG has to equal 0. And finally, CF plus GH has to equal 1. This is a system of linear equations. So it feels a little bit weird to think of it this way, but we can write out a matrix and find its reduced row echelon form to solve for E, F, G, and H. So to do that, the first column is going to represent the E. So from the first equation, I get A times E plus 0 times F plus B times G plus 0 times H must be equal to 1. The second row is going to be 0 times E plus A times F plus 0 times G plus B times H must be equal to 0. The third gives me C times E plus 0 times F plus D times G plus 0 times H has to equal 0. And finally, 0 times E plus C times F plus 0 times G, 0 times, G plus D times H has to equal 1. And that looks like I wrote a G when I meant to write a D over there. Okay, so now we can find the reduced row echelon form of this. And I'm going to do this rather quickly, skipping some steps because I want to have the space to do this. In fact, I'm going to go ahead and put a midpoint step here, and then I will erase this before I actually move on because I'm going to use this whole space. If I think about what these columns represent, these are the E, F, G, H, and answer columns. And so when I go to find the reduced row echelon form, I'm going to take the first row and divide it or multiply it by 1 over A to get 1, 0, B over A, 0, 1 over a. The second column, I'm also going to multiply by 1 over a to get 0, 1, 0, b over a, 0. The third column, I'm going to multiply by 1 over d to get c over d, 0, 1, 0, 0. And the fourth, I'm going to multiply by 1 over d to get 0, c over d, 0, 1, 1 over d. So this isn't quite following the algorithm that we used before, because I just went ahead and made all of my pivot positions be equal to 1 in this step, which is a little bit different than the algorithm, but it will work for us. Now I want to simplify this a little bit. So the first two rows I'm going to leave alone. So 1, 0, b over a, 0, 1 over a. And 0, 1, 0, b over a, 0. And then the next line, I'm going to take and subtract c over d times row 1 from this next row. That gives me a 0, 0, and then the 1 minus, sorry, minus not plus, c over d times b over a gives me bc over ad, and then 0, and then we have a, we're taking negative, subtracting c over d times the first row, so that gives me a 0 minus, or just a negative c over ad. And for the last row, let's make this just a little bit bigger. I'm going to get 0 when I take the c over d minus c over d times the second row. I'm going to get a 0, then a 0, and then a 1 minus bc over ad. And for this last spot, I'm going to be taking my 1 over d, and I'm subtracting 0 times b over c, so that becomes just a 1 over d. So that was going through that very, very quickly. If you're not comfortable with those, you can work it through much more slowly and work out all the details. But I'm going to just go ahead and erase this midpoint matrix because I'm going to use that space. So now I'm not going to go all the way to reduced row echelon form. It's a lot more effort to do that than I want to do. What I'm going to do instead is I'm going to read off my the answers from the last row and work upwards. So that last row tells me that 0 times E plus 0 times F plus 0 times G plus 1 minus BC over AD times H is equal to 1 over D. So I get 1 minus BC over AD times H is equal to 1 over D. Well, this is going to be a trick that I use again and again. I'm going to replace that 1 with AD over AD. So this becomes AD minus BC over AD times H is equal to 1 over D. And all I've done is replace the 1 with AD over AD so that they have common denominators and do the subtraction of the fractions. So AD over AD minus BC over AD becomes AD minus BC over AD. Then I'm going to multiply by AD and divide by AD minus BC to get that H is equal to AD, but then I'm going to have that over D. So it's just going to, those are going to cancel. I'm going to have A over AD minus BC. So I now know what H is equal to. Then I'm going to repeat this process. So this is for finding H. Let's repeat this process to find G. So reading off the second to last row, I get that 1 minus BC over AD times G is equal to negative C over AD. I can find common denominators and put on the left-hand side, I can get AD minus BC over AD is equal to G. Sorry, times G is equal to negative C over AD. Multiplying by AD and dividing by AD minus BC gives me that G is equal to negative C over AD minus BC. Let's do this again to find F. To do that, I'm reading off the second row. So I get 1 times F plus B over A times H is equal to 0. But I know what H is because I calculated that above. So F plus B over A times, my H is A over AD minus BC has to equal 0. And now I can cancel my A's, and I'm left with, and then if I subtract that to the other side, I'm left with F must be equal to B over, negative B because I subtracted it, negative B over AD minus BC. And finally, let's go back and figure out E. So E, reading off the first row, gives me that E plus B over A times G is equal to 1 over A. But I know what G is, so I know that E plus B over A times negative C over AD minus BC has to equal 1 over A. Now I'm going to let's see. Now I'm going to do a little bit of simplification. So when I do that, I'm going to get, this becomes E minus BC over A times AD minus BC has to equal 1 over A. I'm going to multiply this right-hand side by AD minus BC over AD minus BC. So all I've done is multiply it by 1. And so that gives me that E is equal to, on the right-hand side, AD minus BC over A times AD minus BC plus, because I'm adding the BC over A times AD minus BC to the right-hand side, so that gives me plus BC over A times AD minus BC. Now I have common denominators, so I can add the fractions together to get E is equal to AD minus BC plus BC is just AD over A times AD minus BC. And my A's cancel, so I get E is equal to D over AD minus BC. What this tells me is if A is equal to A, B, C, D, then the inverse matrix is that E, F, G, H matrix is equal to, well, all of E, F, G, and H have a 1 over AD minus BC, which is just some number. So I'm going to pull that out front. Times the matrix, well, E was D over the AD minus BC. F was negative B over the AD minus BC. G was negative C over the AD minus BC. And H was A over the AD minus BC. And so A inverse, we have calculated A inverse. However, this only works if AD is not equal to BC. Because if AD is equal to BC, then the 1 over AD minus BC becomes 1 divided by 0, and that's not defined. So we can now have an inverse matrix for this 2 by 2 matrix. That was a lot of work for the simplest matrix to work on. So in the next video that I publish, I will show you faster ways, better ways to come up with these inverse matrices. But this gave us a starting point. The next question then would become, why do we care? So let's go ahead and look at why this matters. So if I'm looking at the matrix equation AX is equal to B, this matrix equation has a unique solution. If A is invertible, so if A inverse exists, then we can take and we can multiply both sides of this equation by A inverse. The problem is matrix multiplication has to be done in the correct order. So A times A inverse is the identity, and A inverse times A is the identity. So from that perspective, it doesn't have to, but A times X is going to be a vector, not a matrix, and that vector, that single column vector times A inverse isn't even going to work in a nice way for us. So what we are going to have to do is do left multiplication. It's important that we put it on the left-hand side. But if we take this equation and we multiply on the left-hand side by A inverse, what we get is A inverse times A times X is equal to A inverse times B. But A inverse times A times X, I can rewrite as A inverse A times X, which is equal to A inverse B. A inverse A is the identity, so that becomes the identity matrix times X is equal to A inverse B. But the identity matrix times X is just X. So X is equal to the A inverse times B. So if the inverse matrix of A exists, if I know what that is, I don't have to go through the whole process of doing my reduced row echelon form. I can just multiply on the left-hand side by A inverse. What's more, this A inverse B is the only solution To see that it is the only solution, let's assume that you've got some other solution, so that x equals some other solution, u is a solution. That would mean that a times u is equal to b. And if we multiply both sides of this on the left by A inverse, I get A inverse times A times U is equal to A inverse times B. But that is the same as A inverse A times U is equal to A inverse B, or the identity matrix times U is equal to A inverse B, or U is equal to A inverse B. So every solution is just this A inverse B, which means if A inverse exists, there is exactly one solution. And that solution is that x is equal to A inverse times B. So if you know the inverse of the matrix, it is very, very quick and easy to find the solution of the matrix equation. So when the inverse of the matrix exists, then the solution is really super quick and easy to find. A few things to talk about there's a few things to talk about in terms of how these matrices are, how we think about these matrices. So one is, if A is an invertible matrix, then A inverse is also invertible, and A inverse inverse is equal to A. So I can take the inverse of A inverse and get back to A. The next is if A and B are square matrices, so that when I multiply them together, I get some other square matrix, and that square matrix is invertible. Then A and B are also invertible, and AB inverse is equal to B inverse times A inverse. And finally, if A transpose is an invertible matrix, then A is also an invertible matrix, and A inverse transpose is equal to A transpose inverse. I'm not going to go through the proof of that, but it is the case. We are going to spend time talking about how to know when inverse matrices exist in the next video, but I wanted to spend just a little bit of time figuring out how to find an inverse matrix. So let's do a quick way to find an inverse matrix. So if we have a matrix, a square matrix, let's say 1, 1, 2, 1, 3, 4, 0, 5, 5. Hopefully I don't believe I made any mistakes. I believe that one will be invertible. If I want to find the inverse of that, if that's my A, to find the inverse, we are going to build a matrix by taking A and the identity matrix and putting them side by side. And so what I mean by that is we are going to build the matrix that starts the first three columns, 3 because the A is a 3 by 3 matrix, are just A. And then the next three columns are the identity matrix. Some people like to put a little dotted line here. You can, but you don't have to. This, I'm going to find the reduced row echelon form. The reduced row echelon form. When I find the reduced row echelon form, I will get a matrix that looks like the identity A inverse. So let's go ahead and do that. I think it's easiest with an example. So let's take and find the reduced row echelon form of this matrix. To do that, I've already got in the first row, the first position is a pivot position that is equal to 1. So I'm going to just leave it alone. And I'm going to replace row 2 with row 2 plus a negative 1 times row 1, which gives me 1, 1, 2, 1, 0, 0. And then I take negative 1 times that and add it to the second to get 0, 2, 2, 0, 1, 0. Let's be careful. That would be negative 1, 1, 0. And 0, 5, 5, 0, 0, 1. And I can already tell you I made a mistake because this matrix is not going to be invertible. But let's go ahead and keep going just so we can see what happens when the matrix is not invertible. So I'm going to scale row 2 by 1/2 to get 1, 1, 2, 1, 0, 0, 0, 1, 1, negative 1/2, 1/2, 0, 0, 5, 5, 0, 0, 1. And I'm going to replace row 3 with negative 5 times with row 3 plus negative 5 times row 2. When I do that, I get 1, 1, 2, 1, 0, 0, 0, 1, 1, negative 1/2, 1/2, 0, and 0, 0, 0, 5 halves, negative 5 halves, 1. And this is the problem. I've got a row that in the matrix is 0, 0, 0, so I'm never going to be able to turn that and get that into a form that is going to work for me to get me into that first start becoming an identity matrix. So this is problematic. So what we can do is we will do this example with a different matrix. So this time we're going to use as our matrix A. Let's use 1, 2, 3, 1, 3, 4, 0, 5, negative 1. And hopefully I didn't make a mistake this time, but we will find out. So I start by writing this out as 1, 2, 3, 1, 3, 4, 0, 5, negative 1. And then I add 1, 0, 0, 0, 1, 0, 0, 0, 1 as an identity matrix at the end. Now we just find the reduced row echelon form. To do that, we're going to replace row 2 with row 2 plus negative 1 times row 1, which is giving me 1, 2, 3, 1, 0, 0, 0, 1, 1, negative 1, 1, 0, 0, 5, negative 1, 0, 0, 1. Now, I'm going to take, now I have my pivot position in row 2 is the one that I want it to be. So I'm going to use that to zero out everything below it. So I'm going to replace row 3 with row 3 plus negative 5 times row 2. And I might as well go ahead and zero out everything above it as well. So I'm going to also replace row 1 with row 1 plus a negative 2 times row 2. And when I do that, I get 1. 2 plus a negative 2 is 0. 3 plus a negative 2 is 1. And then 1 plus a negative 2 times negative 1 is 1 plus 2 is 3. And then 0 plus a negative 2 times 1 is 0 plus a negative 2 is negative 2, 0. The second row stays the same, 0, 1, 1, negative 1, 1, 0. And the third row I'm getting by taking negative 5 times row 2 and adding it to the third row. So I get 0. 1 times negative 5 is negative 5 plus 5 is 0. 1 times negative 5 is negative 5 plus a negative 1 is negative 6. Negative 1 times negative 5 is 5 plus 0 is 5. 1 times negative 5 is negative 5 plus 0 is negative 5. And 0 times negative 5 is 0 plus 1 is 1. Now I'm going to scale the third row by negative 1/6. So row 3 is getting replaced by negative 1/6 row 3. And that gives us 1, 0, 1, 3, negative 2, 0, 0, 1, 1, negative 1, 1, 0, 0, 0, 1, negative 5/6, 5/6, negative 1/6. And now I have to zero everything out above the 1 in the third row. So I'm going to replace row 1 with row 1 plus a negative row 3. And I'm going to replace row 2 with row 2 plus a negative row 3. I'm going to write this a little bigger because we're going to have lots of fractions now, and this is something that frequently happens, usually happens. But I'm going to get 1, 0, and then I'm taking negative 1 times row 3, so I get negative 1 plus 1 is 0. Then negative 5/6 plus 3, negative 5/6 times negative 1 is 5/6 plus 3, or 5/6 plus 18/6. 5/6 plus 18/6 is 23/6. Then negative 2 plus a negative 5/6 is negative 12/6 plus a negative 5/6 is negative 17/6. And 0 plus a negative 1 times negative 1/6 gives me a 1/6. That's the first row. The second row is going to become 0, 1. Then 1 plus a negative 1 is 0. Negative 1 plus a negative 1 times negative 5/6 is negative 1 plus 5/6 is negative 1/6. And then 1 plus a negative 5/6 is 1/6. And then 0 plus negative 1 times 1/6 is 1/6. And then 0, 0, 1, negative 5 sixths, 5 sixths, negative 1 sixth. So A inverse, assuming I haven't made any mistakes along the way, A inverse is 23 sixths, negative 17 sixths, then 1 sixth, then negative 1 sixth, then 1 sixth, 1 sixth, negative 5 sixths, 5 sixths, negative 1 sixth. And that is my inverse matrix. That is the process to follow. So the good news is once you know A inverse, the matrix equation becomes easy. The bad news is the process of finding A inverse is not easy. It's very similar to the process of solving the matrix equation. What this does do, though, is once I've found the inverse matrix of A, I can solve lots of different matrix equations that involve that same matrix A as the multiplier. All right, we will talk about how we figure out whether a matrix is invertible or not in the next video. That's it for this time.